Yeah, I was going to say, I've done one pico balloon. I've probably done about a dozen weather balloons until the Weather Service stopped doing them in Denver. And we are, Edge of Space Sciences is now on balloon number 377. Started in 1990, and let's see, there we go. Started in 1990 with amateur TV folks. And they said, what are we going to do with this TV? Well, let's put it on a balloon. And then somebody said, do you think we ought to track it? Yeah. So, well, I Googled, on the left there, you can see that I Googled balloons and radios, and Amazon offers some radio balloons for sale. But, but what I wanted to talk about was some of the radio issues that we run into. Now, we do a program almost entirely of amateur high altitude balloons, latex balloons, goes up to 100,000 feet, pops, comes down on a parachute. It's about 90 minutes up, about 45 minutes coming down, and it usually goes somewhere between 50 and 75 miles out into eastern Colorado. What we do is support STEM school programs, university aerospace programs, high school programs. So what we're doing is flying probably a dozen payloads that students have made. They weigh about 1 kilogram each. The FAA regulations say that if your payload string weighs less than 12 pounds and no one piece weighs more than 6 pounds, which I think is the size of a goose, you can fly with very few regulations. If, however, you exceed that, there are regulations that you have to meet, but you can fly a balloon and there's no weight limit on that. And we generally are flying balloons that are larger than 12 pounds. We used to have a variance from the FAA that said we could fly it up through clouds. A few years ago, they took that waiver away from us. So now, if it's cloudy, we have to split it up into 2 12-pound payload strings. If it's clear, we can do 1 large balloon. But we send the balloon out into the field, and then we take the students out there and we go out and recover the equipment. We're interested in getting our equipment back. The students are interested in getting their payloads back. In 377 flights, we've never failed to recover any balloons. A couple of them took a couple of months until the farmer finally found them in his field, but we count that as being recovered. So there's a picture of the students lined up with the balloon. We have them hold their payloads and launch them. And even though Phil said nobody should be using APRS anymore, we always have 2 APRS beacons on our balloons for redundancy purposes, and we are now also flying an ADS-B, which is the aircraft beacon, and the flight controllers can actually see it on their screens. If you fly the exempt balloons less than 12 pounds, you technically don't have to contact FAA, but we go through the whole we contact them a week in advance, 3 days in advance, 24 hours in advance, 5 minutes in advance, and we go through that process even with the exempt balloons. Now, you can launch your own balloon. A single person, you can fill up your balloon, put some sort of a radio beacon on it and launch it, and go out, and if you've got a tracking mechanism, go out and recover it. And your chances of doing that are pretty good. We, however, do larger balloons, have a organized program that does happen months in advance, working with the schools. Poor Man's Space Program, I think Bill mentioned that. The big balloons that we use start out about 9 feet tall. They're probably 8 feet in diameter. The burst diameter on that balloon, I think, is rated at 47 or 47 feet in diameter. So as it goes up, what's really neat is as it goes up, If it's blue sky, it gets larger, and the white against the blue sky, you can see it with a naked eye at 100,000 feet. There's the flight profile. It's pretty linear going up and then exponential coming down because the parachute comes down as a function of air pressure. And there's the blue dots are the every 30-second beacon tracked out into the field. If you're going to do your own, or if you're going to do a balloon and you want to recover it, there's a couple of things you need to do. Proper prior planning prevents poor performance. I think there's another P in there somewhere. I'm not sure what that is. But habhub.org has some prediction software on it that you can run, and you can estimate how much gas you need to put into the balloon to go up at a constant rate or go up at a known rate. And then once you know the rate you're going up, there's some software that will take a look at the wind models that the Weather Service publishes and show you where the balloon's going to go. And one of our keys to success is we use the predictions to get our tracking and recovery team out in the field prior to the balloon coming down. And about 50% of the time, we can get the students out in the field as well. And so if they can launch the balloon and then we can get them in the cars, take them out in the field, they can see the parachute coming down, and then the landowner will let us walk the kids out in the field to pick up the balloon. That's really neat. They're very enthusiastic and get to participate as much as possible in this thing. So that's pretty good. Yes, question.
Why do you let the balloon pop? Why not just vent the gas when it gets too, the pressure gets too high and let it keep going around?
Well, he said, why do we let it pop? We want it to come back down within range where we can pick it up. If we went with a floater type balloon that did continue on, the likelihood of recovering the student payloads is zero. And most of the student payloads do not have radios in them. They have data loggers in them. They collect, ultraviolet and temperature and particulate and that sort of thing. But they're collecting the data, and they have to recover the balloon in order to recover their payload.
There's a good example. You're flying under VFR rules, FAA says you're supposed to be visual, but where do you even go through Cirrus clouds or 30 miles down the road there might be a cumulus bank?
Well, his question is what do we have to, if we're flying VFR rules and we do run into clouds? The regulations say you shall not fly through clouds with less than 5/10 visibility, cloud cover. So in the morning we get up and I look at the cloud prediction models and the air stuff, but the aircraft prediction stuff. But in the morning we go out there and we look, and if it's clear and where we're going to be flying down to the south is clear, we go ahead and fly. If it's not clear, we then go to the exempt balloons, which do not have the cloud requirement. But we put our teams out into the field, and we typically have on the order of 4 to 7 vehicles going out in the field. One of our people is the tracking and recovery coordinator, and we all communicate using ham radio to talk to each other. And we also track the balloon in that we all have APRS equipment in our cars, computer that collects the data, puts it on a map, and so we can see what's going on. So communications gets to be important. One of the primary things that we use is repeaters out in the field. One thing nice about Colorado is we've got some really tall mountains just to the west of us. And there's some repeaters up on Pikes Peak, for example, at 14,000 feet. It's a hell of a tower. And we can use that repeater quite a ways out into the eastern Colorado. There's also a couple other mountains that have repeaters that we typically use. If we get out of repeater range, we switch over to simplex and communicate amongst ourselves with simplex out in the field. We have a ground station that we leave at the launch site, and that ground station serves a couple of purposes. Number one, a couple of purposes. It eye-gates the information from the balloon back onto the internet. And the reason we do that is because we have a site on the internet that shows the maps and the balloon performance, and all the kids can bring that up on their smartphone and track the balloon as we go out in the field. So they can see essentially the same stuff we're seeing in the car on their smartphones, and that's really valuable. Once in a while, some of these college students will take off in their car on their own, and that gets a little scary as far as interfacing with the landowners and things like that. But most of the time, it works out real well. The other thing is our ground station guy. He's sitting in the comfort of the truck in his bunny slippers and can look at what's going on in great detail. Right now, the guy that's doing it actually is a PhD in aerospace, so he's the right guy to be doing this. But he can look at it, he can predict, computers are predicting where it's going to land, but he can fine tune that, radio that information out to our tracking and recovery coordinator, and then he can put things out. So this is a big operation, but I just wanted to talk a little bit about this. Another neat tool we have, Rocky Mountain Ham in Denver has put together a DMR network. Actually runs along the continental, or the Front Range, Continental Divide, clear from Cheyenne, Wyoming to Albuquerque, New Mexico. And they let us use their system for DMR or communication. So we actually have two modes of communication. And the DMR system that they have set up actually works better than the mountaintop repeaters when we get out in the sticks. So most of us have DMR capability in our cars as well that we use for that. But if all else fails, cell phone coverage. Actually, when we first started doing eastern Colorado, there was a lot of dead space where there was no cell phone coverage. Over the years, things have gotten better, and once in a while, I'll get a cell phone call from the Alpha, the tracking and recovery coordinator, just because it's easier than fighting everybody on the radio. Yes, sir. Question.
This only work in open country. In the Northeast, all you would see is trees. Looking for this thing.
Yeah, well, the communication would work just as well. Yeah, we're lucky in eastern Colorado. It's all grass plains, and almost always lands on the ground, once in a while in a power line. That's a different issue. But like Bill said, if you're out in the east, you're likely to land in a tree, and then you got to deal with the trees. And
Still find them.
you can usually find them because they'll still be beaconing. And the best thing is when it lands, you can still hear the beacon. You'll get a latitude and a longitude. You can actually put that into your handheld GPS and get the kids together and hike out. You going to shoot me when I run out of time?
No.
Okay.
I just wanted to make a short comment.
Short comment.
When I was out in the Edge of Space Sciences for one of the Great Plains Super Launch events, it's wide open spaces, prairie land, no trees. My balloon landed in a cornfield, which is one of the worst places you can land. They somehow found a cornfield in Colorado. They came back, the chase team came back, and it had a ear of corn stuck in my payload.
Okay, so that was the kind of radio that we're using on the ground. Yeah, question.
What type of ADS-B transmitter are you using that's lightweight enough to fly on a balloon?
Oh, you're beautiful. He asked, what kind of APRS transmitter do we use? ADS-B. I'll show you a picture of one. ADS-B, the aircraft transmitters, were pretty big and pretty power hungry until they were required on UAVs, drones. All of a sudden now they've got really small. Unfortunately, they haven't gotten really cheap. But as far as APRS, let me talk about that first. Over the years, it started back in 1991 with directional antennas and people out in the field, and the tracking and recovery coordinator would position people out in the field. We had a grid system that we said where we were. He would triangulate and use a grease pencil to draw on a map where the balloon was. When we went to started using ADS-B, some people quit because it wasn't fun anymore. But we were using GPS units, using TNCs, and radios. The Elinco DJ C5 was a credit card size radio. We were using that. Then we used some of the smaller HTs. I forget if they were Yaesus or what. But now what we're using for radios are these radio modules that the Chinese make. And it's actually a circuit board radio. Probably can't see the block diagram down in the bottom, but it has all the pieces to do CTCSS. They're usually both VHF and UHF, or maybe you buy just one of the bands, but it's got a microphone in, it's got audio out. You do have to have an external if you want to use it as a radio. In fact, this is the module that's in the Baofeng. And so that leads immediately to the question of what about spurs on it? And as it turns out, it does need to have a low-pass filter built into it to meet the FAA specs. I'll show you a picture of that in a minute. But we've used APRS. I think Phil was talking about this horse binary. We haven't used that to date, but a horse binary is being used more and more. We have flown amateur TV, and we've had students that have tried to fly radio, commercial stuff like Wi-Fi, Bluetooth, and LoRa. So we've had all of those various things. There were some students just recently flew LoRa and were receiving packets back down from the balloon at 100,000 feet pretty reliably. Okay, somebody was asking about the ADS-B. As the ADS-B got smaller, for the drones, you can see what the size of that is. That used to be about $2,500. And you need to have a special one that will go above 18,000 feet. A lot of them, the GPS will stop at 18,000 feet or not go any higher. So we have to get a particular model that does. And unfortunately, the price of those has now gone up to about $5,500. And so part of it is these are certified for FAA flight on aircraft. And I don't think we actually need that certification, but that's what we get. So at the moment, we've got 2 of these units. We'd like to get a third one, but we haven't gotten the finances to do that yet.
Quick question, how hard would it be to DIY those?
DIY, the APRS, the ADS-B, the aircraft? I don't know. I don't know exactly what it is. I'm told that puts out a 50 nanosecond pulse at about 250 watts. Okay, 3 minutes left. Okay, so building the beacons, we've got that's a picture of what our beacon looks like. We package it up. We use these things over and over again. So it's packaged up with a solid plastic top and bottom on it that will withstand as it hits the ground. The rest of it is foam core to keep it lightweight. The board is custom built by a couple of our members, has a GPS, has a the radio on it. It has communications, another module on it to communicate with other parts of the balloon payload string. On the back, you can see the processor. And this guy actually, instead of buying a TNC, he programmed his own TNC software into this thing. It's got a memory card up on top of it to keep track of the data. But when we get the whole thing done and put together, it does have to have the low pass filter built into it, and designing that was an exercise. It was pretty interesting, but he finally ended up, if you look on the far left, you can see the peak, that's the primary, and on the far right, you can see the third harmonic, which is down about 67 dB or something like that, well below the 40 that's required, so it worked. And then the mechanical build of these things, if you're gonna fly, and some of these have flown over 100 times, the mechanical build, it's all circuit boards that are bolted together, very few connecting wires between the two of them. Student payloads that fail is almost always because their connecting wires aren't soldered well or don't connect well together. So we have worked, some of the guys in our group have worked very hard making a solid unit. But that's kind of the big picture on a program that uses these beacons over and over again and flies lots of balloons. So that's what I've got to say. I will be around afterwards for any additional questions. Thanks.